Drum. My name is Zhu Sanxiao, comes from National Central University in Taiwan. Here is my outline. I will talk about some introduction and the motivation, paper review, and the experimental procedures, and then the results and the discussions, and last conclusions. And as we know, the particles are everywhere, like sand dune, the coffee beans, nuts, pharmaceutical debris flow, and so on. I'm in mechanical engineering, so we are very care about the particle technology in the engineering and especially in industries, including the pharmaceutical manufacturing, the chemical synthesis, and the coating, and also milling, metallurgy, food industry, cement. So the motivation of this study, as we know, the granular segregation are very important and is a very important subject of great interest to scientists and engineers. But the mechanism of size-induced segregation is studied by many researchers. But the density-induced segregation receives relatively less attention. So for this study, we will focus on density-induced segregation. And talking about rotating drums, most study focus on the cold segregation. And the understanding about the mechanism of strict segregation patterns is still poor, particularly in the density-driven system. So I will focus on density-driven strict segregation in a rotating drum. So we will study the density ratio, the rotation speed, and the fill-in level on the effect of this on the strict segregation patterns. So here I quick review 4 papers. The first one is by Max. They pour the mixture of larger and the smaller particles from this side, and and then they found the streak, and they conclude that if the large grains have larger angle of repose than the smaller ones, the streak forms. If the large grains have smaller angle of repose, then segregation occurs but no streak. Okay. Sorry. For here, the white are small particles. Okay. And then the second is by Miller et al. They reporting the causing of radial streak patterns. As we see here, again, the small particles are black. Okay. So for initially, it's like this, and after they rotate like 10 revolutions, they found the streak. And they continue to rotate, the streak become coursing, and the last become like this. So they indicate that coursing seems to be driven by transport of small particles from streak to streak through the semicircular radial core. And then the third paper is by Hill et al. And then they reported that the fill-in degree, fill degree means how many particles we put inside the drum. Okay, the fill-in degree has a significant influence on the cutoff of waveness, which is related to low-pass filtering in a rotating drum. So the p squared divided by a, I will explain later, but you can see this represent how many streaks exist in the drum. So the d over r, d is the r is the center of the drum, d is the distance here. So d divided by r can represent the fill-in degree. If d is minus, which means the fill-in degree is less than a half. Okay, so the most highest number of streaks happen in this point is roughly larger than 50% of fill-in degree. Okay, and this is by Zhang et al. They use 2 different material or particles. One is glass beads, one is steel beads with different diameters, so different combination. For example, this is 3 millimeter and 1 millimeter, 3 millimeter and 2 millimeter. So they have all kinds of combinations. And for this region, they find mixed. The flow are mixed. For this region, it's coal segregations. This region is contain coal and also a band. And for this region, they found streaks. Okay, but all their study, including Heat et al., Jen et al., Knaha et al., all shows that streak formation occurs in size different system. They did not find the streak segregation in density different, but with the same size of particles. So for this study, we use a similar drum. The radius is about 25 centimeter. The thickness is about 9 millimeter. All particles are 3 meter, diameter are 3 millimeters. We have 4 kinds of particles. One is stainless steel, one is glass, one is POM and PP. Here are their densities. So we can use different combinations, making different density ratios. So we have 4 combinations. So the density ratio ranging from 1.57 to 8.81. And we use different rotation speed from 0.6 to 1.4 RPM. We also use different filling degree ranging from 0.45 to 0.61. Before the experiment, we put heavy particles and light particles with the same volume and a half and a half. Then we rotate the drum in about 20 RPM. So the coal segregation roughly from here. Of course, because the sizes are the same, so the coal segregation are not so clear. But we can see they are more, the white are glass beads, so it's heavier particles. The red are PP beads, so they are lighter. So the lighter particles are more of gathered in the surrounding and in the top free surface. So after the coal formed, we stop the drum, and then we start with this different rotation speed, which is much less than the 20 RPM. So in these conditions, the streak may form. So I'm talking about the this parameter defined by here, which is p squared divided by a. As we see, here we are streaks. So we have some image analysis and become something like this. And then the p is the perimeter of the streaks. Okay, so the length. And then the A is the area surrounded by the perimeter. Okay, so the p squared divided by A indicates if this number is large, it means there are more streaks. If it's less, it means less streak or almost no streaks. So this number can be characterized the number of the streaks and the type of strips. So here is one movie. We use 0.8 RPM, the filling degree of 51%. And the glass beads, heavier particles, are white, and the PP are red. Okay, so this movie is about 4 minutes, so we may see the change. Before we run this, as I mentioned, there are not, actually this is, we can call it coal segregation, but not very clear here. The heavier particles get here, and the lighter particle are here and here. So when we move it in 0.8 RPM, we can see this layer will avalanche and together somewhere here. Okay. So when it moves to here to the repose angle, so the rate comes here, so we can find it start together like this. And it seems this time is red, and then it's white, and then red, and then white. And we can see roughly pattern forms. And then the streak will become clear and clear. So usually for about 1 to 2 revolutions, in this case, the streak formed. But for some case, it goes maybe like 5 or 10 revolutions. And for this, actually, it's interesting to look at this part because it's a flowing layer. So what kind of particles avalanche also depends on the dynamic repose angle. So now here are very clear, right? And for red particles, as I mentioned, they are lighter particles. And for lighter particles, they have larger repose angle, larger dynamic repose angle. Okay. And for heavier particles, by here, they say because the wave breaking mechanism, making the white particle will move faster than the red particles and come to here. So from here it's clear and clear because the white come from this streak, and then the red come is from here. But for white, it will penetrate to the center. But for red, it's only up to here. So I may stop here. So this is different time snapshot. We also enlarge this part so that we can see clearly from this image. And as I mentioned, for this part, it's very interesting. So we also grab some image to analyze. And this is the so-called wave breaking mechanism. We can see for some case, this part here are lighter particles. Here are heavier particles. And because the center is here, so it rotates like this. So for here, the particles avalanche have higher velocities. So here move faster and faster. So this interface become parallel like this. And eventually, the lighter particle move to this side and the heavier particle in this side. And then they continue to avalanche. Here have higher velocity. So heavier particles have higher velocity. So it becomes just like the wave breaking and form these. And this continue for each avalanche process. And we also look at this region, and we use PTV to measure the average depth of heavier particles and the average velocity of heavier particles. We can see this is the velocity of heavier particles, and the position, the depth from here, the depth of the heavier particles. We can see it's very periodically change. Actually, this from here to here is just like one avalanche. Okay. So similarly, and we try to use different rotation speed and to check the shape index And we find with higher rotation velocity, the shape index become less, which means less or smaller number of streak formed. So we can see here 0.6 RPM, 1 RPM, 1.4 RPM. And then we, this is the number of streaks formed, and this is rotation speed. As I mentioned, higher rotation velocity, we have smaller number of streaks. And also, if we have higher density ratio, we also have smaller number of streaks. And then we measure the angle of repose, dynamic angle of repose. For here, we also find the density ratio for higher density. We have smaller dynamic repose angle. And for we see here for higher rotation speed, we have higher repose angle. And then we calculate the difference of dynamic repose angle of lighter and heavier particles, non-dimensionalized by the repose angle of lighter particles in the vertical axis. And this axis is density ratio. So we can, by all our experiment tests, we find that if the density ratio is smaller than some certain point, roughly like 1.6, it's always mixed. And 1 minute. And if density ratio higher, and the repose angle difference is not big enough, it's called segregation. And if it's big enough, the streak pattern forms. Okay, so this is the perimeter plot with passage of the time, which means this is a wavelength, and the time from here move to here, we call t. T is here, so it's linearly increased with t. And we also find the with 51% filling degree, we have highest number of streaks. Okay, here come to my conclusion. Thanks.
I have a question. So if I understand correctly, if you have a different density and a different angle of repose, then you get the streak segregation. And if you take the, if you have the same angle of repose, then you have coarse segregation. So I'm trying to visualize what will physically be different at the interface where the avalanches occur. Is it not individual avalanches anymore, but is it a continuous avalanche for coarse segregation, or can you comment on that?
Yeah, I think the dynamic repose angle are very important. So they must have different repose angle to form.
If they're zero, what's happening physically different that you only have coarse segregation? Instead of intermittent avalanche.
You mean for coarse segregation?
If you have different densities with the same angle of repose, you're stating you get coarse segregation only, right?
Yeah, but I think if we have two density particles, but if their repose angle are the same, the streak won't form.
Right, but then my question is, what's physically different? Do you still have intermittent avalanches, or what's happening at a free surface?
What's happening in free surface?
I'm just trying to understand it.
Yeah,
maybe you could. Right, that's okay. You don't have to. You know.
Yeah. Okay.
So that's fine. Is there any other question? Maybe I suggest that you get together and
okay
and talk about the physics of that.